Congratulations, you made it back for video 3 for Unit 5. And this is where we will actually take a look at the processes involved with linear programming. We'll focus on some phrases that you might not have heard. It's possible this is new to you, but it's not painful. It's not difficult. The bottom line is we got to read a word problem and create some inequalities and then process the graphing skills that we've hopefully already developed. So let's share the PowerPoint. Let's move across and see how this looks. All right, video 3, firing at you. This is the notion of linear programming. The notion that we're looking at is to create some kind of a function that in effect we want to maximize or possibly minimize. I would kind of think probably in a business environment, we might be looking more to maximize profits or maybe minimize losses. So I guess we could see minimum sneaking in as well. All right, it's a process that you and I will have to run through. Uh, what we need to do is we need to create constraints in an objective function. The objective function is what we seek to maximize or minimize. We're going to have to graph the system of constraints. That's my inequality system. That's what we've been working on so far together in this unit. The feasible solution region, or the area of feasibility, the region of feasibility, is simply the solution to that system of inequalities. All right, then we'll get all the corner spots, all the vertex locations. We'll fire each of those ordered pairs for the corner spots into the objective function. We'll find out what maximizes or minimizes that function that we seek. It sounds pretty verbose. It sounds very complex. It's not that hard to do. All right, so here's a problem for us to look at as an example. So the Red Cross is going to send some aid. You got an earthquake, it's bad. All right, so they're going to send medical kits, they're going to send water. All right, you've got some constraints in that the plane can only do so much. It can only carry so many pounds and it only has so many cubic feet capacities. So those are restrictions on the problem, constraints, if you will. But we do know this, that every medical kit we send can aid 6 people, and every container of water can aid 10. And the bottom line is we want to maximize the number of people that we can aid. So how many of each of those things that we send will be dependent on the solution to this linear programming problem. All right, so let's take it through step by step and see how we would approach the solution of this word problem. So as we go through these slides, the word problem is going to be showing up in the text box. Goal number 1, we got to represent some unknowns. I'm old, I use X and Y. So it doesn't matter whether X tracks the number of medical kits or whether X tracks the number of containers of water, but we have to reference which is which. So in the context of our solution, I let X be the number of medical kits we send, and then I let Y represent the number of containers of waters that we send. Someone may have spun those differently, in which case their inequality set would have looked different. All right, but that's the most important thing. What are your letters doing? Put it down there so people can follow it. Step 2, what kind of restrictions are we looking at? Well, obviously we can't send less than 0. There's no such thing as -5 medicine kits. So your first inequalities are the fact that both X and Y can't be negative. You can't send negative of either of those. So inherently, you've got 2 constraints that you see listed on the right side of your screen that basically says that. I either have to send none or some. I can't send a negative amount of either. So those are kind of lurking. Sometimes you won't have those because we might have a problem that says you have to send at least 5, in which case you'll have an inequality that doesn't necessarily need the 0. Okay? So those are kind of trivial, but they're significant nonetheless. Well, if we look at it in terms of space, the plane can only hold 6,000 cubic feet. And if you read the problem, we realize that each medical kit takes 1 cubic foot of space, and each container of water also takes 1 cubic foot of space. So you can kind of envision those ones as coefficients for both X and Y. I kind of wish I'd picked a problem where something had taken more than 1 cubic feet, like pretend that it said 2 cubic feet of space for water. You would add 2Y, representing 2 cubic feet needed for each. So in this case, it's just X plus Y, 1 for each X, 1 for each Y, and that total has to be less than or equal to 6,000, which is my maximum capacity in terms of cubic feet. There's another constraint here based on weight. The plane can carry at most 80,000 pounds. Here I did a better job. Each medical kit takes 10 pounds worth of weight. So that's 10 times X. Each container of water needs 20 pounds or takes 20 pounds. So that's 20 times Y. And again, over on the extreme left side, you see I keep reminding us what each of these X's and Y's are representing for our solutions of the problems. So kind of on a step-by-step process here, you and I have built what we're going to call the system of constraints. It's a system of inequalities relative to the verbiage contained in that tan text box. Okay. If you're really ahead of your game, you can make your numbers a little smaller. If you don't mind dividing everything by 10, I'm on board for that. Let's do it. Haven't changed that set of restrictions so much as just modified the look to smaller numbers. So that's how that guy sneaked in, even though when you read the problem, you don't necessarily see a 2 or you don't necessarily see an 8,000. But I still think it's a good attack. Make your numbers smaller tends to make your life easier. All right. System of constraints. What do you got for us, man? Well, I got those. I couldn't send negative amounts. So those first two inequalities were, hey, I'd either send none or some. And then those last two inequalities were constraints based on space relative to cubic feet and relative to weight based on pounds. So as we get ready to graph that system, that's where we left off last video. All right, so your next step would be to go ahead and graph that system of 4 inequalities on one grid. Okay, and we'll get to that momentarily. But this objective function talks about what it is we want to maximize. Well, we want to maximize the care that we can, the number of victims we can help. Now, honestly, I don't know about NV for number of victims. That's kind of yucky. You might have just said P for people or V for victims or H for helped. So I'll let that for you in terms of what you choose for that left side variable. But again, if you read the problem, it tells us we can aid 6 people with each medical kit. We can aid 10 people with each container of water. So there's our objective function wherein we're going to try to maximize the number of victims we can aid based on the satisfaction of that system of constraints. And that's going to be the objective function we seek to maximize. So we're going to get ready to graph the system next, and then we'll proceed with the solution based on the ordered pairs for the feasible region. That we'll look at in video 4. This is the end of video 3, wherein you and I have reached our objective function and we have developed our system of constraints. So in the next video, we'll look at the graphs of that system and we'll figure out how to decide what values maximize our objective function. See you soon for video 4.